Hello and welcome to Controllers Tech. Today we will continue with part 5 of the STM32 custom bootloader series, where we take the next step forward. In the previous part of this series, we saw how to use a button to trigger the OTA update process. At that time, the bootloader did not flash any OTA image. Instead, it only cleared the OTA flag, printed a message, and blinked the LED in an infinite loop to show that the process was running. Today we will flash an actual OTA image from the bootloader, which means we will now update the firmware properly. We will first generate a binary file for the application, and then flash that binary file using the bootloader. Since the basic concept has already been explained in detail in the previous 4 parts of this series, today I will focus more on making the whole process practical and closer to a real-world use case. I am going to make several changes to the previous approach, so it is important to watch this video carefully and follow each step. Here I have loaded both the projects inside STM32 Cube IDE so we can work with the application and the bootloader together. Let's start with the application project first, because this is the firmware that will be updated. As I mentioned before, the application header will be written by the bootloader after the OTA image is flashed. Because of this, we can set all the elements in the header structure to 0 inside the application project. The application does not contain any metadata inside it. Instead, we will calculate that information later and attach it to the application binary file. Although the OTA flag is still being used, we cannot remove this application header completely. For this reason, we keep the header structure even though most of the values are set to 0. We do not need to make any other changes in the application project at all. You can simply treat this project as the application image that needs to be flashed by the bootloader. The new application will only print data to the console and blink the LED every 5 seconds, which makes it easy to confirm that the update worked. Build the project, and the application binary file without the header will be generated in the project folder. Open the project folder and then go inside the debug folder where the output files are stored. Here we already have a Python script that was used earlier to calculate the CRC of the application binary file. Delete this file and copy the new Python scripts into the application folder. The new app final Python script now calculates the CRC and the size of the application, and then appends this data directly into the binary file itself. By doing this, we no longer need to manually update the application header, since everything is handled automatically. You can change the application version every time you run the script to represent a new firmware version. The final output file will be named OTA-image.bin, which is the file that will be flashed by the bootloader. Run this script, and the new binary file will be created in the same folder. This file is 7736 bytes in size, while the actual application size shown in Cube IDE is about 7.54 kilobytes. The extra size of this binary file comes from the metadata that we have added to it. This metadata is 16 bytes long and contains only 4 32-bit words. We also have another Python file in this folder for the next step. This script is used to convert the binary file into a C header file format. In today's video, we are not implementing any automatic way to upload the binary file to the STM32, so we will copy this C header file manually. In later parts of this series, we will directly send the binary file to the STM32 using either a TCP server or an HTTP server. That is why I created 2 separate scripts, one to generate the binary file and another to generate the header file, instead of putting everything into a single script. After generating the header file, copy it and paste it inside the bootloader project. That is all we need from the application project for now. Now we will move on and start modifying the bootloader project. Here we need to make a lot of modifications to the files that were created earlier in the previous setup. I have prepared new OTA and flash operations files specifically for this project. Let's copy the source files into the source directory, and the header files into the include directory. You can overwrite the old files in these folders, since we will no longer use the previous versions. Let's start by looking at the flash operations.c file first. I have modified the function so that it now reads the OTA flag directly from the application header. The OTA flag is the first element in the header structure, so we can read it directly without any extra processing. Next, there are three important functions in this file, one to erase the entire application, another to erase only the application header area, and a third one to write a single word into flash memory. I have written these three functions separately in this file, so you only need to update them based on the flash memory layout of your specific MCU. These functions are written for page-based flash memory, but you can also modify them for sector-based flash if your device uses that type. All the flash-related changes need to be done only in this file, and the rest of the code will continue to work without any changes. Now let's take a look at the OTA.c file. This file has been completely rewritten compared to what we used in the previous video. At the beginning, we have a set of CRC functions that will be used later to verify the data. The function check OTA request reads the OTA flag from flash memory, and returns 0 if the flag is set, meaning an update is required. In a similar way, we also have a function to erase the entire application, which internally calls the corresponding function from the flash operations file. Inside the main bootloader file, we will call the function OTA run, and this function will decide which other functions to call based on the current OTA state. The parameters passed to this function are the OTA context structure and the OTA stream structure. This function will first read the OTA header, which is the metadata that we stored earlier in the application binary. Then it will verify the magic number and also check the application size that is stored in the metadata. Next, it will store the actual application image size inside one element of the stream structure. This image size represents only the real application data, and does not include the metadata that was added to the binary. After that, it will call the OTA begin function to start the OTA flashing process. This function will first erase the entire application memory region. Then it will store all the required information inside the bootloader context structure and initialize the CRC calculation. A running CRC is used here, which will be updated every time a new data is written into flash. Once everything is initialized, the actual flashing process will begin. The code will read the data in small chunks from the provided memory location and write it into the application flash region. At the same time, the CRC value will be updated for every chunk that is written. After all the data has been written to the application flash memory, the OTA finalize function will be called to complete the update process. This function will now finalize the CRC calculation, and compare it with the expected CRC stored in the application metadata. If everything matches correctly, it will write the application header into the header section of the flash memory. Basically, it will clear the OTA flag and then write the magic number, application size, CRC, and application version. So this completes the full OTA process, starting from reading the file, writing the data into flash memory, and finally validating and finalizing the application. Inside the OTA.h file, you will find the stream structure. This structure is very important because it is responsible for handling the OTA application file. This structure contains two function pointers. The read function is used to read the data from the provided OTA image file. How the data is read depends on where the OTA file is stored. We will discuss this shortly. Since the application size is not known to the bootloader at the beginning, the function setTotalSize is used to update the size variable. We call this function inside BL-OTA run after extracting the application size from the metadata. Now we need to define these functions inside the main file. The memory base variable will hold the starting offset of the application image. This is useful if you are storing the application in external flash or some other memory. In this case, since we are reading it from a header file, we can leave this value as 0. The memory cursor will keep track of how many bytes have been written to the application flash so far. The total size variable will be updated later after we read the actual application size from the metadata. For now, we need to provide an initial value, which should be the size of the application metadata. The application metadata consists of 4 words, so I have provided 16 bytes as the initial value. The function OTA setTotalSize will update the application size after it is read from the metadata. Next comes the most important function, OTA read. This function reads the data from the given memory location and updates the related variables. This is the main part where you will need to make changes based on your system. For example, if the application is stored in an external flash, the memcopy call here would be replaced with code that reads data from that flash. If you are receiving the data from a TCP server, this function would instead use something like TCP receive to get the data. So in simple terms, you only need to modify this function depending on how and where the OTA data is being read from. Inside the main function, we will first check if the OTA flag is set. If it is set, we will start the OTA flashing process. Remove the clear flag function, because the flag will now be cleared automatically when the bootloader updates the application header. First, we need to define the required functions for the stream structure. Next, we create a bootloader context structure and then call BL-OTA run to start the OTA flashing process. If the OTA update completes successfully, this function will return 0. If it fails, we will print the appropriate log message and stay inside the bootloader while blinking the red LED to indicate an error. If the OTA is successful, we will print a success message. After that, the bootloader will verify the application by checking its header, and if everything looks correct, it will jump to the application. Inside the OTA read function, I am passing the OTA image array that we generated earlier in the application project. Let's include this OTA image header file here and build the project once. We also need to include the string.h file, because it is required for memory operations like copying data. We still have some errors in the project, and one of them is related to the definition of AppMagic. This variable is currently defined inside the bljump.c file, so we will remove it from there and instead define it properly inside the application header file. Alright, the major errors are now resolved, but we can see that the flash memory has overflowed. This was expected because we are using around 7 kilobytes of the application file inside the bootloader project. To reduce the flash usage, I am going to comment out all the UART logging functions. For now, we will depend only on the LED indications to show whether flashing was successful or not. Alright, there are no more errors, and you can see that the flash memory is now almost full. Even though it is tight, we can still continue working with this setup for testing. Do not make the application too large for this test, otherwise it may not fit. Later, we will implement a proper solution to handle this limitation. Our bootloader is now ready, so we can either flash it directly from the IDE or use the Cube programmer. Connect the SD link to the programmer, go to the download section, browse for the bootloader binary file, set the address to the start of the flash memory, and click Start Programming. Note that we are not flashing the application project at this stage. We have only flashed the bootloader, which will flash the application by itself. Open the serial console so that we can see the logs. Disconnect from the Cube programmer and reset the board. The application is running correctly, and the LED is blinking every 1 second. Now press the button to trigger the OTA update. The board resets, the bootloader takes control, it flashes the new application, and then jumps into it. You can see that the LED is now blinking every 5 seconds, which is exactly how we programmed our application. You can also see the logs showing that the new test application is running. Now let's test the entire process one more time. I am going to create a new application that blinks the LED every 100 milliseconds. Build the project so that the new application binary file is generated. Open the debug folder and edit the script to update the application version. Now generate a new OTA image.bin file and then create the header file that contains the data array. Copy this new header file into the bootloader project. Build the bootloader project and flash it directly from the IDE. The board will reset, but it is still running the old application. You can see that the LED is still blinking every 5 seconds. At this point, connect the board to the Cube programmer and check the application version inside the application header. You will see that it is still running version 3. Now press the button to trigger the OTA update. The bootloader will flash the new OTA image and then jump to the application. You can now see that the LED is blinking every 100 milliseconds. You can also see the logs showing that the new application is running. If you connect the board to the Cube programmer again, you will see that the application version is now 4. This confirms that the new application is successfully running on the STM32. So we are now able to flash the OTA correctly from the bootloader. If there are any errors during the flashing process, the bootloader will not jump to the application. In order to debug any issues, you can run the bootloader in debug mode. To do this, first erase the entire flash memory, and then manually set the first word of the application header to 1. This will set the OTA flag and tell the bootloader that an update is required. Now go to the bootloader project and start it in the debugger. Since the OTA flag is already set, the bootloader will immediately start flashing the OTA image. You can now step through each function one by one to see exactly where a problem may be happening. In most cases, the error may be due to a CRC mismatch, so make sure to check that part very carefully. So now we have seen how to flash an OTA image from the bootloader. However, the process is still not complete, because right now we are manually copying the file into the bootloader project. We need a fully automated way to handle the application binary file. In the final system, the application will download the file from an HTTP or TCP server, store it in internal or external flash memory, and then set the OTA flag. After that, the bootloader will flash the OTA update and jump into the new application. This will remove the need to manually copy any files into the bootloader project. We will cover all of these steps in the next videos of this series. That is all for this video. You can download the complete project from the link given in the video description. Leave a comment if you have any questions or doubts. Keep watching, and have a great day ahead.